大家好，我们今天接着来看 CS50 C 语言基础这节课剩下的一点内容然后首先是我们这个运算符，就是我们在编程的时候有时候要做一些计算，然后前面4个是我们非常熟悉的一个4则运算的运算符号然后最后这个百分号可能平常大家接触的比较少，它是一个取模求模的符号它是英文的这个 modulus然后前面因为是 mod， 所以叫它求模的一个符号。它实际做的操作就是取余数比方说这里有一个简单的例子13对4取模，它就是13除以4，然后等于3余1此时我们 m 得到的是1这个余数然后这个求模在编程中有一个简单的应用场景，就是我们通常用它来判断一个数是不是偶数我们可以用让这个数打比方有个变量 x， 然后对2取模然后看它是不是等于0，如果等于0其实就是能不能被2整除，等于0的话它就是偶数然后否则的话它就是奇数，一个简单的小应用接下来看老师来讲一下接下来
Calculate the remainder when you divide one number by another. In fact, why don't we go ahead and use these in a very simple program and make our very own calculator. So let me go over here to VS Code. Let me go ahead and create a new file called calculator.c. And in this file, let's go ahead and first include a couple of now familiar header files, CS50.h as well as standardio.h. Let's go ahead then and declare main with int main void. And then inside of main, let's do something relatively simple. Let's declare an int and call it x and set it equal to whatever the return value is of getInt, prompting the user for a value for x. Let's then give ourselves a second variable. We'll call it, say, y. Set that equal to the return value of another call to getInt, prompting the user this time for that value y. And then let's very simply go ahead at the very end and just print out, say, the sum of x plus y, a super simple calculator. So I'll use printf, quote unquote, %i for integer, \n, to give me the new line. Then I'm going to go ahead and do x plus y to indeed print out the sum. Let me go down to my terminal window now. Let me do make calculator in order to compile the code. No error messages, so that's good. Let me do /calculator, and let's do something like 2 plus 2, which of course should equal 4, and it does. But it turns out that sometimes there are going to be limitations that we bump up against, and let me get a little more ambitious here. Let me clear my terminal window, and let me go ahead and rerun calculator again, and this time let's type in 2 billion for x, and let's type in the same for y, and of course now the answer of 2 billion plus 2 billion should of course be 4 billion. And yet it's not. So curiously, we see of all things a negative number here, which suggests that somehow the plus operator doesn't quite work as well as we might like. Now, why might this actually be? Well, it turns out that inside of your computer is, of course, memory, or RAM, random access memory, and depending on the size of your computer and the type of computer, it might very well look a little something like this, a little circuit board with these black little modules on it that actually contain all of the bytes of your computer's memory. Unfortunately, you and I only have a finite amount of this memory inside of our computers, which means no matter how high we want to count, there's ultimately going to be a limitation on how we can count because we only have a finite amount of memory. We don't have an infinite number of zeros and ones to play with. We have to actually be bounded ultimately. So what's the implication of this? Well, it turns out that computers typically use as many as 32 bits, zeros or
好，这里刚才老师他往2个整形里面存了一个非常大的数之后让它相加然后它的结果并没有我们所预料的出现一个正确的答案，而是它变成了一个负数那这里发生了一个问题，就是我们的整形溢出问题然后这里就是为什么呢？因为我们老师刚才讲的，就是我们计算机它的内存是有上限的然后我们就不可能无限制的去存储一些东西，然后我们对这些类型它能存储的最大的位数是有规定的然后像我们整形的话，它的一个规定的存储的一个范围是32位32位它能二进制的32位，然后它能，因为我们既要有负数又要有正数，那把两边平均分的话，它能代表的一个范围就 一个范围就是负的2的31次方，然后到这个正的2的31次方减1，然后我们还有一种叫无符号的整形无符号的整形它就是没有负数从0开始，那此时它也是32位的话，它能代表的一个范围就是0到2的32次方减1那这里其实无符号跟有符号它的整形的区别就是我们这里我们通常来说我们会用假如说后面还有 n 个0，然后我们通常会用第一位作为一个符号位然后这样的话它就是假如说第一个是0，那代表后面的这一串二进制它代表的是正数，然后如果第一个是1的话，代表后面的这一串二进制它是负数然后这样的话因为我们把第一位拿走了作为那个符号位之后我们因为我们是32位来表示嘛然后后面就只剩下31个位这样我们有符号的整形它就只能是2的31次方，因为它只有31个位而我们无符号的它又这最前面的这个0它也可以参与进来它不需要一个符号位，这时候它的最大的值就可以到2的32次方减1它是这么来的。然后我在这边有一个简单的程序可以给大家看一下，就是当我们整形溢出了以后，一般会发生一个什么样的情况然后我这边定义了一个 i， 它是最大的这个正数最大的整形int max 就是代表最大的整形，它是定义在 limits h 这个库里面的，我们可以点过来看一下然后它实际定义了以后，它是一个这一个东西，然后我们可以看到它就是2的这个31次方减1这个数应该是没毛病，应该是一样的然后它这里其实定义的也是一个常量，但是它是我们 C 的预处理器去定义的可能会跟平台有关。然后我们实际在使用的时候假如说要定义一个最大的整形，我们实际在使用的时候不要直接用这一个常量，而是要用 limits h 这个里面定义的，因为这一个它是跟平台有关系的然后这时候我们定义了以后，我们来看一下这个加1之后它会是什么情况然后同样的这个 uint max 它就是这个无符号的整形的最大值然后我们可以来看一下大家可以看到这个首先是打印这个 int max 它就是2的31次方减1然后加1了以后它会发生一个什么情况呢加1了以后它跑到这边来了，它变成了这个整形范围的最小值就是最大，它相当于变成了一个循环从最大值跑过来变成一个最小值这也是老师刚才2个正数相加会变成一个负数的原因。然后这边 uint max 它是2的32次方减1对，然后加1的话它也是跑过来加1的话它也是从这边跑过来变成了一个最小值0就是我们整形如果假如说它溢出的话，通常的编程语言它都会是这么一个情况就是从另一端重新开始对，然后就是我们这个 printf 我上次之前也应该说过，就是我们这个 这个占位符啊，它需要根据这个类型改变的如果是有符号的有符号的整形，它就是百分号 D。当然，如果是我们无符号的整形，它应该是一个百分号 U 才能输入出就是正确的数字。这是要提的一个小点。然后接着如果我们整形溢出了，但是我们需要做更大数的计算的话，我们需要换一种能储存更大数值的类型接下来可以看老师讲一下这个。
Concern. Well, C does not have just integers or ints. It also has longs, which, as the name suggests, are just longer integers, which means they have more bits available to them. So let me go back into my code here. I'll clear the terminal window, and let me go ahead and change my integers to literally long here, long here. I'm going to have to change my function in CS50's library to be not getInt, but getLong, and that's indeed another function we provide in the library. Let me change this getInt to getLong as well. I'll keep my variable names the same, but I do need to make one other change. It turns out that printf also supports other format codes, so not just %i for integers or %s for strings, but also, for instance, %li for a long integer, as well as %f for floating point values with decimals. So with that said, let's go ahead and change my printf line to be not %i, but %li. Now let me go ahead and do make calculator again, enter, no apparent errors now, /calculator, and 2 plus 2 still equals 4 as before. But now if I do calculator again, and let's do 2 billion again, as well as 2 billion for y, previously, we overflowed the size of an integer and got some weird negative number because the pattern was misinterpreted, if you will, as a negative number instead. But a long, instead of using 32 bits, conventionally uses 64 bits, which means we have more than enough spare bits to go when we add 2 billion plus 2 billion. And now, in fact, we get the correct answer of 4 billion, which does fit inside of the size of a long. Now, a long can count up quite high, and in fact, it can count as high as this, 9 quintillion, and so that will give us quite a bit more runway, but of course, it too is ultimately going to be finite. So if you have numbers that need to go bigger than that, you might still very well have a problem.
这里就是我们把整形换成了一个长整形，这个 long。int 换成了 long， 这样它就能存储更大位数的，我们就可以去进行更大位数的数字之间的计算然后接下来老师会提这个精度丢失的这个问题。
Now, there's another problem that we might run into as well, and we can see it in the context of even this simple calculator. Computers also suffer from, potentially, what's called truncation, where especially when you're doing math involving floating point values, that is numbers with decimals, you might accidentally, unknowingly, truncate the value, that is lose everything after the decimal point. So in fact, let me go back to VS Code here. I'll clear my terminal window, and let's still use longs, but let's go ahead and use division instead of addition here. So let me change this plus to a divide operator. Let me go ahead and recompile the code down here with make calculator. Let me go ahead and run /calculator, and let me go ahead and do something like 1 for x and 3 for y, and we'll see that, well, wait a minute, 1 divided by 3 I learned should be 1/3, but in a floating point value, that should be 0.333333, maybe with a little line over it in grade school, but really an infinite number of 3s. And yet we seem to have lost even one of those 3s after the decimal point because the answer is coming back here as just 0. So why might that be? Well, if I know that two integers, when divided one by the other, is supposed to give me a fraction, a floating point value with a decimal point, I can't continue to use integers or even in this case longs, which do not have support for decimal points. So let me go ahead and change this format code here from %li to %f, which is again going to represent a floating point value instead of a long integer or even an integer. And let me go ahead further and define maybe a third variable, z, as a float itself. So I'll give myself a variable z equals x divided by y, and now rather than print x divided by y, let's just go ahead and print z. So now I'm operating in a world of floating point values because I know proactively that a long or an int divided by another such value, if it's meant to have a fraction, needs to be stored in a floating point value, something with a decimal point.
这里刚才老师对这个 x 输入了一个1，然后对 y 输入了一个3，然后因为这两个它其实都是整形所以它出来的这两个相除，它出来的它并不是0.33，因为它相当于两个整形相除，它对应的类型也是整形，所以它把后面的小数点后的数字都丢掉了，所以1除以3变成了一个0。然后这时候老师要做的一个是什么呢？他是要把这个结果变成了一个可以存储小数的一个浮点型，然后这个相对应的占位符也变成了这个百分号 f， 用来打印这个浮点型，然后我们接下来看会发生什么。
Well, let me go down to my terminal window here and rerun make of calculator. Seems to work okay. /calculator, and let's do 1 divided by 3 again. And still here, we see all zeros. So we do at least see a decimal point, so we've made some progress thanks to the %f and the float, but it seems that we've already truncated the value 1 divided by 3. So how do we actually get around this issue? Well, if you, the programmer, know that you're dealing in a world that's going to give you floating point values with decimal points, you might very well need to use what's called a feature known as typecasting. That is, convert one data type to another by explicitly telling the compiler that you want to do so. Now, how do I do this? Well, let's go back to my code here.
这里出来的虽然带了小数但是因为这两个数它还是整形，所以它在进行除法运算的时候，它这个精度已经被丢失掉了。然后这时候我们需要在计算之前先对它们做一个类型的转换。
Here, and if the issue fundamentally is that C is still treating x and y as integers, or technically longs, with no decimal point, and dividing one by the other therefore has no room, so to speak, for any numbers after a decimal point, why don't I proactively do this? Let me, using a slightly new syntax with parentheses, specify that I want to convert x proactively from a long to a float. Let me specify proactively that I want to convert y from a long to a float as well. And now let me go ahead and trust that in Z should be the result of dividing not a long by a long or an int by an int, but rather a float by a float. Let me clear my terminal window, run make calculator again, seems to work okay, /calculator, and now 1, 3, and hopefully now we actually see that my code has outputted 0.333333 and
像这样把这个 x 前面加一个括号，然后对应的类型把这个 x 这个整形转换成一个相应的浮点型然后这样这两个浮点型的数相除以后，它就可以正确的输出这个浮点型的结果。但是并不是所有的类型都可以用这个括号然后就直接对应的转化过来的这个还是得看具体的情况比如说正常情况下我们不可以直接把字符串跟这个数字这样直接转换，类似的情况。
And I think if we kept showing more numbers after the decimal point, we'd theoretically see as many of those 3s as we want. But there is still one more catch, and especially when we're manipulating numbers in this way in a computer using a finite amount of memory, another challenge we might run up against, besides integer overflow, besides truncation, is this known as floating point imprecision. Just as we can't represent as big of an integer as we want using int or long alone, because there is going to be an upper bound, there's similarly going to be a boundary on just how precise our numbers can be. And indeed, let's go back to VS Code here. I'll clear my terminal window yet again. And this time, let me use some slightly unwiggly syntax to specify that I don't want to see the default number of numbers after the decimal point, which %f gives us automatically. Let's go ahead and show me 20 decimal point numbers after the decimal point. And the weird syntax for this is to do not %f, but %20 to indicate to C that I want to see 20 digits, not the default after now the decimal point. Let me rerun make calculator. Let me do /calculator again, and let's do 1, let's do 3, and now this is even weirder, right? From grade school, you presumably learned that 1 divided by 3 is, of course, 1/3, but that should be 0.33333 infinitely many times, or on paper with a little line over it. but the computer is just doing some weird approximation in here. It's a whole bunch of 3s and then 4326744079590. Well, what's really happening under the hood? Well, again, is this issue of floating point imprecision. If you only have a finite number of bits, and in turn a finite amount of memory, the computer can really only be so precise intuitively. Equivalently, the computer has decided on some way of representing floating point values, but the catch is, per grade school math, there's an infinite number of numbers out there and an infinite number of floating point values because you can keep adding more and more digits if you want. So the computer, given the way it's implementing these floating point values, is essentially giving us the closest approximation that it can. Now, how can we go about improving the situation? Well, there is one alternative. Instead of using float, I can use something called a double, which is the name suggests.
这里啊，就是我们用像这样把这个占位符改成一个点小数点，然后后面跟上位数，我们就可以显示出小数点后的多少位这个样子。然后老师刚才改了以后发现这个结果并不精确那同样是因为这个类型的精度的问题然后此时老师打算把它换成一个精度更高的这个 double， 把这个 flow 换成这个 double， 然后我们看一下会发生什么。
Jest uses twice as many bits as a float. So instead of 32 typically, it will use 64, and that's just like the difference between a long and an int, which gave us more bits, but in this case, this will be used for more precision. Let's go ahead and cast x to a double. Let's cast y to a double, and now let's go ahead and using the same format code, %.20f is still okay for doubles. Let me do make calculator. Let me do /calculator, and now let me do 1 divided by 3, and we still have some of that imprecision, and we'd see even more of it if we looked at more than just 20 digits, but now we have more 3s after the decimal point, so it's at least more precise. But it's not perfect, but it's at least more precise. So these kinds of issues then are going to be necessary to keep in mind anytime you do something numerically, scientifically, at least with a language like C, where you're going to bump up against these real world limitations of hardware and in turn language. Now later in the semester, we'll transition to a language called Python, and that's actually going to solve at least one of these problems for us, but just automatically giving us more bits, so to speak, as we need them, at least for integers. But even the issue of floating point imprecision is going to remain. Now,
这里虽然 double 提高了它结果的精度但它实际上还是会有一点点的那个不准确然后后面假如说我们学到了那个老师说我们学到 Python 或者说我们去学其他更高级的语言，可能我们不用去做这种类型转换等这种这么繁琐的工作，因为这个语言它自动的帮我们处理了一些这个问题当然像这种计算的一些精度的问题还是仍然存在的，就是有时候我们即使用其他更高级的语言，还是要注意这种就是大数之间的计算之间的这种问题。
Just how real world are these issues? Well, back in the year 1999, we got a taste of this when the world realized in the years leading up to that date that it might not have been the best idea to implement computers and software therein by storing years using just 2 digits. Like instead of storing 1999 to represent the year 1999, a lot of computers, for reasons of space and cost, were in the habit of kind of cutting a corner and just using 2 digits to keep track of the year. The problem with that is that if systems were not updated by the year 1999 to support the year 2000, 2001, and so forth, is that just like before with integer overflow, some computers might add 1 to the year in their memory, 99. It should be the year 2000, but if they're only using 2 digits to represent years, they might mistake the year, as some systems may very well have, for the year 1900 instead, taking literally a big step backwards, if you will. Now, you'd like to think that kind of issue is behind us, especially as we understand all the more about the limitations of code and computing, but we're actually going to run up against this very same type of issue again in just
这里老师介绍了一个我们以前非常经典的一个千年虫的问题就是以前90年代的时候，人家一些计算机系统它去记录这个年份的时候，可能只用了2位数就是99年这样子，然后到2000年的时候它往前一跳这时候2位数变成了00 那计算机系统可能会误认为这个时间是1900年，这就是我们一个计算机史上一个经典的千年虫问题，大家有兴趣的话也可以课后再去了解一下。然后这节课这么长的这节课用了正课然后包括我们一些短视频的内容就我在视频里面都有相关的介绍，然后大家可以再回顾一下，然后把尝试去做这个练习题，还有实验题，还有作业，然后接下去我会继续讲这个作业，然后谢谢大家。